So we've seen how the molar Gibbs energy for each of the phases, solid, liquid, and vapor, can vary as the temperature varies. And a diagram that we produced a little while ago, it looks just like this diagram that is shown on the right here. And I'll remind you that the solid phase is the one that has the least slope, then the liquid phase, then the vapor phase, and the 2 points that are indicated on here are the intersection points where a phase transition occurs. All of this is drawn for a constant value of the pressure. But the question we want to address in this video is what happens as we change that constant pressure. In other words, how are these curves affected by viewing them at a different pressure? To get a handle on this, we want to consider the fact that the molar Gibbs energy as a function of pressure, so the partial derivative with respect to pressure at constant temperature, is equal to the molar volume. So what we're going to want to see is how this molar volume is going to change as we change this for each of the 3 phases. Now I'll note that our molar volume for a vapor is typically much larger than the molar volume for a liquid, and that's about the same, maybe a little bit bigger than the molar volume of a solid in most cases. There are some unusual cases in which the molar volume of the solid is greater than the molar volume of the liquid, water being the principal example. All right, so we know that these things are going to change, it's going to shift, but what this the fact that it's positive means is that the Gibbs energy, the molar Gibbs energy, also the chemical potential, is going to increase as pressure increases. So that gives us a very good clue as to how these curves are going to shift. Now I want to illustrate this for each of the phases individually, and then we'll come over to this pre-drawn curve and see how it looks when it's all put together. So if I have the solid, and I want to draw how this is changed, okay, this is the Gibbs energy of the solid and temperature. And if this is my initial curve coming down slightly like that, how will it look if I increase the pressure? Well, the molar volume of the solid is the smallest of these, so we'll expect to see the smallest change. I'm going to emphasize that by making this only a very slight change, but there will be a slight change upward. So it'll create another curve that's slightly above this curve, but there won't be a big shift when we go to that new pressure. If we were to look at a slightly lower pressure, it would shift it in the other direction, but again, it would be a very slight shift. So we would expect to see these curves be very close to one another, and so it won't reflect a lot of change when we draw this out on the big picture. All right, what if I do this for a liquid? Well, I'll see something very similar because the molar volume of a liquid and the molar volume of a solid are very comparable. Okay, the liquid slopes down a little bit steeper, so it may look something like this. And now if I draw what this looks like at a higher pressure, it will shift this curve upward, but not by very much. It'll be about the same as what we saw over here for the solid. Similarly, if I shift it to a downward, to a smaller pressure, it'll shift it downward some, but not by a lot. So in both of these cases, I'm using red to indicate a higher pressure and purple to indicate a lower pressure. I should have probably marked that. All right, so we're not seeing a big change for either solid or liquid. What this suggests is that we shouldn't expect to see a big change in the transition, the phase transition of solid to liquid or liquid to solid by changing the pressure. In other words, there's not a huge pressure dependence on the temperature of fusion. What about for the vapor? Well, if I draw a similar diagram here for the vapor, and again, we're drawing the molar volume for the vapor. Okay, it's the steepest curve yet, so it's going to come down quite steeply. All right, how does that change now as I go to a higher pressure? Well, at the higher pressure, we're going to see a much greater deviation from our initial curve, so it's going to be a noticeable bulge outward, if you will, as we do this. And at a lower pressure, we'll see a noticeable bulge inward. All right, so For the vapor, we do see a substantial effect, which means that any phase transition that involves a vapor, either a vaporization or a sublimation, should see a substantial effect when we look at the phase transitions and the positions of those phase transitions. So let's see what this looks like on the big diagram. So what I'm going to do is I'm going to draw this for the solid first, and it's just going to be a slight change, a slight upward change in the Gibbs energy of the solid. But not a major change. Same is going to be true for the liquid. So it'll look something like that. So you can see that the new position of their intersection is not very far removed from the old position of their intersection. In other words, there has not been a large shift from one T fusion, from T fusion at one pressure to the T fusion at another pressure. And we'll see how this is manifest later in phase diagrams, but this is a good lesson that, in fact, in this case, changing the pressure is not going to shift that intersection point very much. But what happens when we look at a gas? Well, in that case now, as we go to a higher pressure, we're going to shift that curve way out here like this. So now what has happened is we started at an intersection point with the liquid here and moved it over to here. So in fact, we see a large change in the temperature of vaporization. So we went from here to here. So in effect, the temperature of vaporization shifted upwards quite a bit by increasing the pressure. All right, we needed to raise the temperature more in order to achieve vaporization. In these cases, you can also see that this has shifted the gas-solid intersection point way out too. Now we don't care about that so much here because the solid doesn't persist over to this intersection point. The solid stops existing after about this point here. But in cases where the gas and the solid do intersect so that we see sublimation, the fact that gas is sensitive to this pressure is going to make a difference for us. But this is a good sort of early indicator as how pressure affects these things, and we're going to see how that influences some other qualities that we see in substances in the next couple of videos.